Our goals for this lesson, for those of y'all that are having to go back and watch this video, you can just pause it and get the goals written down in your book. We are on page 154. So our first goal is I can make sense of rules of function. I have underlined that because we've talked about what a function is and how to represent it in function notation. And now we're going to talk about what it specifically means when it says rules of functions. When they are written in function notation, and then once we do that, once we make sense of the rule, we're going to be able to create tables and graphs to represent that function. This says I can write equations that represent the rules of functions. All right. So in this lesson, we're going to be using function notation to describe rules. This is part 1 of 2. Lesson 5 will be part 2. So first thing we're going to do is a notice and wonder. We have 2 functions here. What do you notice? What do you wonder? So on this side, write notice. This side, you can do your wonders. Now, when you're doing these, make sure the reason they have these specific activities where they have them in the unit is because you're building off of skills that we've already talked about. So what you know about functions, naming functions, all the different parts of function notation, all of that stuff, take into consideration when you're looking at this. Pull back from your previous knowledge when you're doing things you notice and things that you wonder. Okay, make really good observations, not, you know, that there's 4 numbers in the table. Like, do some really good observations. Okay, I'm going to give you all about 2 minutes to come up with those, and then we will come back to this. Ready? Go. Okay, so who has any notices for these 2 tables? Ava, what'd you notice?
The table on the left is function f, and then the table on the right is function g.
Okay, so based on what we know about function notation, we know that this first letter here tells me the name. And so these both have different names. So what does that tell me about these 2 tables?
They're different.
They're whole different scenarios. So we've got 2 different functions, F and G. Good. What else do you know, Sky?
I saw there's 2 different formulas.
Okay, so in these, it gives us these equations in here. Okay, so when we're looking at this table, what part of the table is that equation in?
Y.
The Y or the output. All right, so what I notice is that there is an equation as the output. Interesting, interesting. Luke, what do you notice?
On the first table, where it says x5 and the output is 0.
Mm-hmm.
I used the equation to check out.
Okay, so when we take our input and we plug it into that equation that Kai noticed, it produces the output. Look, so 5 is our x. So everywhere I see an x in this equation, I'm going to plug 5 into it. What's 2 times 5? 10. What's 10 minus 10? 0. Let's try the 1 and see if it works. What's 2 times 1? 2 times 1 is 2. What's 10 minus 2? 8. What do you think we're going to get if we plug in 1.5? Bet we get 7. What do you think is going to happen if we plug in -2?
14.
We'll get 14. So we notice, good notice, when we plug the x into the equation, we get the y. we plug the x into the equation, we get the y. Is that also true for our function of g?
No, maybe, possible.
Okay, this time our equation for g is just x cubed, which just means x times x times x. Okay, we'll start with 0. What's 0 times 0 times 0? 0. What's 1 times 1 times 1? What's 3 times 3 times 3? Interesting. So when we have these functions set up like this in these input-output tables, because that's what this is, our x is our input and the f of x is the output. If we take our input and plug it into that equation, it's producing our output. Good. Anything else that we notice? These are awesome notices so far. Okay, now, what do you wonder? What are our questions? Some of our notices may have answered our wonders, but Connor, what do you notice?
Are the graphs related, or the whatever they are, functions related?
Are the functions related? Okay, so it could be like one of those scenarios with the dog at the pole. One function could represent day 1, one function could represent day 2. Okay, so they may be related. Kai?
The notice kind of answered mine. I said, why are the numbers in order on the right but not the left of the X?
Okay, so why are numbers in order for X column and not Y column? Good, which we kind of talked about because we can choose any X value and it's just going to produce whatever output our equation gives us. Colby?
I just said, like, why don't they use Y instead of the equations?
Okay. Why? Oops, I literally wrote a Y. Why do they use an equation instead of just using Y? These are awesome. This is one of the best notes and wonders I've ever done, by the way.
Just for the
Yes.
question.
Yes.
Can you explain, I can't read that one.
This one?
Yeah.
It said, why are the numbers in order for the X column and not the Y column? So like it's going from the least to the greatest in our X column.
It's doing the same in the Y column.
It is in this one, but in this one, it's not.
Don't mess up typos.
Since the X value is the independent variable, we really can choose any X value we wanted to and plug it into that equation. But depending on what the equation is, that's going to be dependent on, that Y value will be dependent on what that equation is or what we chose to plug in for X. So we could have chose any X value, but the Y values are dependent on what we chose for the X. Last one, look.
Like, are there 2 different graphs and what they represent?
Okay, so that kind of goes with that first one. Are they related? Like, what are we talking about in those? Awesome. Good discussion. Now we're going to be talking about those more as we move through this lesson. But the biggest thing that I wanted y'all to notice, and we did discuss it, was this about the input and output. I'll go back. That third notice, it said when we plug the X into the equation, we get the Y value, and we're going to be practicing that a lot in this next activity. Okay, moving on. I'll give y'all a second. Give me a thumbs up when y'all ready to go to the next activity. Cool beans. Here we go. Cool beans. 4 functions. How many functions are we working with? 4. Here are descriptions and equations that represent 4 functions. So we've got function f, g, h, and k. Okay, so we have 4. I want y'all to number those off. 1, 2, 3, and 4. How do I know they are all different and talking about different situations?
Different functions,
They have all different what?
different functions.
They are all different functions, but how can I tell that they're all different?
They have different function names.
They have different function names, which is just that letter in the front. Now, they give you an equation to go with each one of these. Now, remember how when we break down a function, we know that that's its name. We know that the number inside of my parentheses is the what? The input. So they all have an input of an X value, which is what we know. And then everything it's set equal to is the what?
Output.
The output. Okay. So all of these different functions have a different output. Okay. So what you're going to do first, and you can do this with a group. I'm going to give you all about 2 minutes. We did this back in 6th grade. I remember, but you're basically putting this little equation into word form. So you're describing what operations are happening and you're matching it to its correct description. Okay. Now be careful with it because look, all of them use a 3 and a 7. Okay. So make sure you pay close attention to the order of operations of which they're happening and then match them. I'm going to give y'all, like I said, about 2 minutes. All you have to do is write the letter next to the equation it matches with, and then we will talk about it together. 2 minutes. Ready, go. People on Zoom, send me your answers in the chat. Okay, thank you.
I can brush my teeth like 3 hours a day. You brush your teeth, why you keep on doing that? No. All right, so you got 4? Okay. You got 4 over there. You got 9, okay? But it's numbered on the side. Oh. God, no, man. Right, yeah, so-
If you finish before the time is up, I can check. Guys at home, remember, send your answers in the chat so I can check them.
Oh, I was supposed to have down the number. I'm already done. Only had those 2 back.
I don't even know how to find.
Do I have them? I did.
Uh-huh.
I didn't answer them all when you asked me. I have?
You had 3 of them, so I knew what they were.
Good, Caitlin. Good, Emily. Good, Jacob. All right, let's look at it. So for f of x, what is its correct description? C. All right, for g of x, what is its correct description? B. And 3, D, and 4, A. Now, the point of this activity was for you to verbalize what was happening to your input to produce your output. Okay, you're literally telling me, all right, in order to get that output, we have to multiply the input by 3 and then subtract 7. So you're just literally telling me what operation you would do to solve it. Okay, so number 1, check, we matched them all. Now, we're going to use these 4 functions for the next 2 questions. So I think you can still see the functions on your in your book when we turn. All right, number 2. It says for one of the functions, for just one of them, so either F, G, H, or K, when the input is 6, underlying input is 6, All right, if the input is 6, what variable did they just tell us? The x. So x equals 6. So when we take 6 as our input for one of those functions, we want to find the one that produces an output of -3. All right, which is our y value. So it says, which is that function, f, g, h, or k? Explain. How are we going to know which function produces this output? We're going to have to plug it in. This is taking all those same skills that we talked about in Unit 2. You have an equation, you have a variable. What do? Plug it in. All right, so let's start with f of x. Let's try to keep this organized. So we have f of x equals 3x minus 7. All right, I'm going to show y'all how to set up a function like this because it's slightly different than how we've done equations. Okay. So again, I got this function from number 1 on the other page. So we have an equation. We have a variable. We've already said we're going to plug it in. Now we plug it in everywhere we see an x. So it goes from f of x to f of 6. And that equals 3 times 6 minus 7. Okay, now, when we have it like this, we are not going to do anything to this part of our function. You can't simplify this side anymore. That's just f of 6. That tells you the name of the function. That tells you the input. So when you're solving it, you just bring that part down. So we have f of 6 equals. Now we can simplify this side because there's 2 operations happening. We have multiplication and subtraction. What do we do first? Multiplication. What's 3 times 6? 18 minus 7 is 11. So for f, when our input was 6, what was our output? 11. Is that what we wanted? So is function f the one that we're looking for? No. I'm not going to mark out my work because all the work is correct. Okay, so if it's not f, let's try g. So we have g of x equals 3 times x minus 7. Very similar, but now we do the subtraction first. All right, let's try it. So we have an equation. We have a variable. What do? Plug it in. So everywhere I see an x, I'm going to replace it with 6. So I have g of 6 equals 3 times 6 minus 7. Can I simplify this side any? Nope. So that just says g of 6. All right, what do I do first? Parentheses or multiplication? What's 6 minus 7?
-1.
What's 3 times -1?
-3.
-3. So when we have an input of 6, this produced an output of -3. Is that what we wanted?
Yes.
It is what we wanted. So g of x is the correct one. We didn't even have to do all 4 of them. Yay. All right, now this next one has 2 parts to it, and they did not give you enough room to do all the parts. So I'm going to show you how to have enough room in your book. Right here where it says, are you ready for more? Mark it out.
Oh, we undid it, so we're not ready.
You are not ready for more there. No, I'm just kidding. Okay, so in order to have enough room, you're going to have, you're going to have part 1 in this top section. And this space down here under the are you ready for more is going to be your part 2 space. All right, so let's look at it and see what they're wanting us to do here. Okay, it says which function value, f of x, g of x, h of x, or k of x, is the greatest, underline greatest, Okay, so it wants to know which one has the greatest output when the input is 0. Underline input is 0. Okay, so when they tell us that the input is 0, what variable did they just tell us? The x. So they told us x equals 0. So how am I going to know which function has the largest output with that input? I'm gonna have to replace the x with the 0, okay? Can I just solve one and know the answer? No, what am I gonna have to do? I'm gonna have to solve all of them and then compare all the outputs, right? Okay, so let's start with the first one, just so I can get y'all started. So we have f of x equals 3x minus 7. All right, I have an equation. What's my input? 0. Okay, so I have f of 0 equals 3 times 0 minus 7. Can I simplify this side of my function? No, so I just bring it down. And now I can simplify this side. What's 3 times 0?
0.
Minus 7?
Negative.
Negative 7. Okay, so there is my output for f of 0. Now you have to find the output for g of 0, h of 0, and k of 0, and then compare. Okay, so that's part 1. If you finish before my timer goes off, there is a part 2. It says, what about when the input is 10? Okay, so what are you going to do all over again?
You're gonna do everything again.
You're going to do everything again, but this time you're going to use 10 as your input.
Sounds so fun.
All right, I'm going to give y'all 3 minutes to do part 1. If you finish part 1, go on to part 2. If you need a calculator, they're in the sink back there. You will more than likely need a calculator for when you get to h of x and k of x, because there's division and stuff.
I'm really good at that.
All right, 3 minutes. Ready? Go.
Wait, you said we were gonna need it.
Yeah, there's one right behind you.
I like watching an episode of Dora.
Hmm?
Like whenever you ask us the questions, it reminds me of Dora. Like, you know, the mountain's like right behind her. She's like, "Where's it at?"
I don't know why, but every time you say ready go, I think of the magic school bus.
It's Miss Red.
Yeah, well, I do. I mean, I know that.
No.
All right, y'all get to work. Y'all only have 2 minutes left. If you think you haven't finished, raise your hand. You want me to check your answers? I can. People at home, make sure you send me your answers in the chat. You can just tell me which one ends up having the greatest output between those 4. Like how to type them in your calculator?
Okay, so you know, we divide a negative by a positive. Is it positive or negative?
It's negative. If there's one negative,
It's only changed to positive when they're both.
when they're both negative.
Wouldn't they just be like the same thing, just like the zero?
No, because they're different equations.
Oh, this is we're gonna have to add. Oh, okay.
Good question though. Okay, those are all correct. Now, which one is the largest? Think of how negative it is. All right, Caitlin, remember how negatives work. I know you have the correct outputs, but remember how negatives work as far as the one, which one's the largest number. Good. All right, let's look at it. You'll get a chance to do part 2 on your own as well, so make sure you're paying attention. All right, so when I have an input of 0 for G, what is my output?
Negative 20.
-21. All right, when my input is 0 for H, what is my output? -7. And then when my input is 0 for K, what is my output? -2.3. Okay. Now, all of those are correct if you did them like that, but remember what the original question was. It says which one is the greatest between those 4. So someone raise your hand and tell me which one is the greatest, Colby. -2.3. Now, a lot of people want to say it's this one because 21 is the biggest number, but you have to remember how negatives work. Okay, so that's part 1. All right, part 2 is the exact same thing. The only difference is what? Our input is going to be 10 this time. Okay, so for f of x equals 3x minus 7, you're going to do f of 10 equals 3 times 10 minus 7. All right, I'm going to give you a little, about 3 minutes. Ready, go. This was so good. We had one live.
I saw, I went to Target, I saw, Maddie.
Yeah, she got there right when we left.
Yeah, I saw her there. That's when my mom saw her the same thing.
All right, once y'all finish with part 2, send in the chat which one is the greatest of those 4. There's my paper. Okay. Sorry, Luke, I'm coming, I promise.
I got a question. Oh, I'm so dumb. I'm so off. I got this one wrong.
Got about 40 seconds left. You don't put the output like that. You have to leave right in something. You have to write it like that, even if you don't throw in your words. You have to write it like that. Yes, sorry, I thought that was a 6. But yes. You're good.
I just tried to write it down close.
Okay, so when the input is 10, what is the output for G of 10? 9. What is the output for H of 10? Negative 3.6 repeating, which you could have rounded to 7. What is the output for K of 10?
One.
1. Sorry, I can't hear anything. Someone else said it. All right, so here are our 4 outputs. So which one of those is the greatest? F. F has the greatest output when the input is 10. Awesome. I don't feel the need to go into a lot of further explanation about this because I think because we spent such a long time going over those types of processes in Unit 2, I feel like this was really easy for y'all to pick up. Okay, so now we're going to take pretty much every single thing we've learned so far in this unit, and we're going to be applying it to this next 2 questions. But the good thing is you're going to be using formulas that you are familiar with. Okay, so we got this. This is the last part, and then we'll take a break. It says rules for area and perimeter. So we're still using those rules or those equations to produce our outputs. So we have a square. I want you to circle square. I want you to circle the word square because it's important that they told you it was a square because there's certain characteristics about squares that we know, okay? Especially when we're dealing with the side length. So I want you to underline side length of 9 centimeters. If we know one of the side lengths is 9, what do we know about all the other side lengths? They're also 9, and then we know that because they told us it was a square. All right, and then they told us that the area is 81 centimeters squared. Okay, so we're going to be working with one side length and the area of we're going to work with one side length to find the area of a square. So the relationship between the side length and the area of the square is a function. 2 underlines. Okay. So it says complete the table with the area for each given side length. Okay, so we're going to do that first. I'll read this little description here in a second. This is going to be what we do first. So we have all these side lengths that they go ahead and give us, and we know that they're in which column? What is this first column always? It's our input or our X. Perfect. Okay. Now, in order to produce the area, we need to remember how to find the area of a square. So who remembers the formula to find the area of a square? What do we do, Ava? We do the length, and I make my L's like this, so it doesn't look like a 1. Okay, length times width. Well, they gave us the length. How are we going to know what the width is? It's the same thing as the length because it's a square. Good. Okay. So we're going to use that understanding to complete this table. Okay. So we have a square and the side length is 1. What's the area?
9.
1.
It's 1.
I'm done.
No, you're just using this 9 also. You did 9 times 1. But that was just an example. Now we're moved on to a different square with a different side length. Okay, so that's centimeters squared. Okay, so if you have a square with a side length of 1 centimeter, then the area is 1 centimeter squared. Okay, now how did we do that? How did we get that area? What did y'all do mathematically? 1 times 1, right? Is that what we all did? All right. Now we have a different square. It has a side length of 2. What's the area?
4.
Not 2, it's
4.
4.
Oh, yeah,
No, you're good. Okay, now I want someone to tell me how y'all did that in your head. You did 2 times 2. Okay, so we did 1 times 1 and we did 2 times 2. Got it.
Right.
So now we have a side length of 4. How are we going to get the area? 4 times 4, which is 16. All right, now what if our side length is 6? We did 6 times 6, which is 36. Okay, now it wants us to get to that rule, okay, or the equation that we would use if we had any side length. What did we do every single time they gave us a side length? We squared it. Okay, or you could have said it, someone else said it a little differently. You multiplied it by itself, so we did s times s, which is s squared. Okay, so however you thought about it, we could represent it both ways. Okay, but for the sake of us all being on the same page, I'm going to use this one. Okay, they're both correct, but I'm going to use that one. Now, so we have number 2. It says once we completed the table, which we did, it wants us to write a rule for a function, A. What do they want us to name this function? A. Circle it. That gives the area of the square in centimeters squared when the side length is S. Underline side length and circle S. We know the side length is our what? We know the side length is our what? It's our input, okay? So what variable is going to go inside of our parentheses? S, okay? So that S value is going to be representing our input or our X value, but they want us to use this variable because it kind of goes more better with this situation. All right, and then we're going to use function notation. Okay, we know what that means. We just have to, we need to make sure we know the name, the input, and the output. So let's write it out. Let's start with the name. What is the name of this function? A. I know that because they literally told me. Okay, so I don't want y'all to think we just made this up. Now we have the parentheses. What always goes inside of our parentheses? The input. What is our input talking about? The side length. And what variable did they want us to use for side length? S. All right. Now, what did we do to our input or our S value every single time to produce our output? We squared it. So we just did S squared. And that's our output. That's the rule of our function. We square the input. So now thinking back to that very first activity we did where they had those 2 tables there and it was just like random equations. To us, now you can see a situation where you've created one of those equations. Wow, so smart. Next, so we've got our function notation. Now it just wants us to ask it's just asking us some questions about our situation. So it says, what does A2 represent in this situation? Well, I see that it's named A. So what are we talking about? This function up here for the area. What does this number on the inside of my parentheses tell me? The input. What's our input talking about? The side length. Okay. So if I were to have A of 2 set equal to something, what would it tell me? Okay, that's what this says, but what if I had it set equal to something, what would that thing that it was set equal to tell me? The area, right? Everything that that's set equal to would tell me the area, right? Okay, so A of 2, you almost had it. You've had everything except for just the output in your explanation. So A of 2 tells me the area when my side length is what? Is 2 centimeters. Did you write that down?
Okay, good enough.
I'm finishing
I'll try to do that. Good enough.
I'm on the.
All right, and then the second question says, what is the value? Okay, so just like we did it all before, if you have a side length of 2, what is the area of your square? 4.
I just spelled week.
There's another question, what do you mean 2 centimeters squared?
If the side length would be 2 centimeters, the area would be centimeters squared. Yeah. Good question. All right, so looking at just this, we can see, not knowing anything else, just based on what we talked about, A tells us we're talking about that square, and we're trying to find its area. We have a side length of 2, so the area is 4. So instead of having to go into that full explanation about it, we have this simple notation, which is really, it's getting easier and easier for us to read. Okay. Now we're going to graph it. Now, don't panic. We turn the page. So we're going to be graphing the function a of s equals s squared. I'm just rewriting it so that when you go back to look at your notes, you know that this graph is from this function. Okay. So once again, we can see based off of our x and y axis, our x values represent our side lengths and our y values represent our area. So I'm just going to use all of these inputs across my axis. Okay, so imagine a square and it has a side length of 0. What's the area? 0. Because it's non-existent.
Yeah.
All right, now, what if we had a side length of 1? What is the area? Remember, what's that operation we're doing with that input? We're just squaring it or multiplying it by itself if that's easier for you to do. So what's 1 times 1? 1. So it's just going to be right there above your 1. All right, what if we had an input of 2? It would be 4. How did we do that? 2 times 2, so it's just a little below the halfway point. All right, what if we had an input of 3? It'd be 9. So it's right below the 10. If we had an input of 4, 16, which is a little bit above the halfway point. It's not going to be perfect, but you see what I'm saying. Halfway between 10 and 20 would be 15, so 16 would just be right above that. All right, what about for 5? 25, so that's right in between 20 and 30. What if we had an input of 6? 36. So it's a little above halfway between 30 and 40. And then we had 7, which is 49, which is right below that 50. Now I'm going to stop there because the 8's going to be off the graph and I don't want to mess up the line. All right, now when you're looking at this, what do you notice about the graph?
It kind of like has a curve.
It has a curve to it. Now, we're not going to really get into that detail right now, but when we go further into functions, you'll learn that this type of function, anytime you have a square in it, your graph will curve. Because it's increasing exponentially, because it has an exponent.
It looks like a ring, kind of like a car. It's like,
Hmm?
looks like it makes our car sound.
Okay,
That's-
all right, last question. This one's gonna be a little bit more, challenging, but I think you'll be fine. There's just an additional, it's a multi-step rule. All right. So we've got a roll of paper. When you're imagining this roll of paper in your head, I want you to imagine like the paper that we use on homecoming, those big rolls of paper. You got it? You got it in your head? Okay, so they even put a little picture in there for you. So it says a roll of paper that is 3 feet wide, underline 3 feet wide. So they tell us the width. Can be cut into any length depending on how you roll the paper out. It says if we cut a length of 2.5, what is the perimeter of the paper? Okay, now I'm a very visual person, so I'm gonna have to draw a picture.
I'm not very good at drawing pictures.
You're just drawing a rectangle.
Wait, is it a rectangle? Because it didn't tell me.
I know it's gonna be some type of quadrilateral, but it has 2 different side lengths, so no, it's not a square. Okay, so I've got this rectangle here, and I know that one of the side lengths is definitely and always will be 3. So if I know this side length is 3, then what do I know about this side length? It's also 3. Okay, now I want to make a little note here that every single rectangle that we're gonna look at for this problem is gonna have a width of 3, just because of how the paper is, okay? If you ever cut any of that paper out, you can always have a different length depending on how much you want, but it will always be 3 feet wide just because that's the paper.
It's top to bottom for Friday Night Lights.
Okay, now it told us the length. What is the length of this paper? 2.5. Now the length will change every time depending on how long you want it. So that value will change throughout this problem. Focus. I want y'all to stay with me for this last bit. Okay, now it wants us to find the perimeter. How do we find the perimeter of anything?
Oh, it's like.
Length times width is area.
All the sides added together.
All the sides added up. So that's gonna be 2.5 plus 2.5 plus 3 plus 3.
That's a lot.
Okay, so basically you're doing the length plus the length plus the width plus the width. And when we do all that, what do we get as our perimeter? 11 feet. Okay, now remember that process that we use to calculate the perimeter, because that's going to lead us into what the rule is later. Okay, so it says complete the table with the perimeter for each given side length. So what is our input again for this table? Side length is our input. Okay, and what is our output? The perimeter. Okay, so this first one, I'm going to draw a little picture and let's see if we can maybe figure it out. So what will our width always be for all of these rectangles? 3. Okay, so I'm just going to draw a little bitty rectangle over here. So I know this is going to be 3 and this is going to be 3. What's my length going to be? 1, because they told me that right here. Okay, so if you need to draw you a little rectangle for each one of these, you go for it. Okay, so what is my perimeter going to be for this one? 8. Okay, now let's try to do this next one mentally. If you need to draw a picture on your own paper, you go for it. This time we have a side length of 2. So how are we going to find the perimeter of that? Which values do not change? The 3. So we have 3 and 3, which is 6. So every single time we know we're going to have at least 6 feet, right? All right. And then what are we going to do with that 2? 2 plus 2. We're gonna double it, right? Okay. So we have 6 And then we do 2 plus 2. So how much is the perimeter? 10.
That's why.
All right, now, how are we gonna do this one? We have 6.3. What are we gonna do with that 6.3? Double it. So that's 12.6. And then we have to add 6, which is 18.6. All right, now we have 11. What are we gonna do with it? Double it, so that's 22, and then we have to add 6, which is, it's a lot of thinking. Okay, now we just have L for side length. What did we do every single time mathematically to these side lengths in order to produce our output? First thing we did was doubled it. Okay, so how do I mathematically show? No, that's
Oh, wait, never mind.
Times 2.
times 2. So how do I show that? What would it look like?
No, it'd be 11 point.
We do,
Or whatever you multiply.
times 2.
It'd be 2 times L, because the side length.
For the bottom, I thought you were talking about the 80.
Okay, now we didn't just double it. What else did we do? We added 3 plus 3, but we can simplify that to 3 plus 6. If you did that, it'd be 3 times 3. But yeah. Okay. Now you could have easily done it like this: L plus 3 plus 3. That's the same exact thing. Okay, we just simplified it. We just said L plus L. Okay, that's 2L. 3 plus 3, that's 6. Right? Okay, there's multiple ways, but like I said, for the first one, for the sake of us all being on the same page, I'm going to use this rule. Okay, now, number 2. It says write a rule for a function P. What's the name of this function? P. That gives the perimeter of the paper in feet when the side length in feet is L. What do they want to use for our input? L, which is the side length. Now it wants us once again to use function notation. Okay, so function notation. When we're doing it, we start with the function name. What is the name of this function? P. All right, then we always do our parentheses. What goes inside of my parentheses every time? The input. What's my input talking about in this problem? Side length, which we use L. And again, I make my L's like this so they don't look like ones. You do not have to make your L's like that, but just so you're not confused, that's why I make my L's like this. My math teachers did it, so that's why. Okay, now we set it all equal to our output. So what did we do to our input every single time to produce our output? What was the rule that we used? Times 2 plus 6. So we just set it all equal to our output rule. So once again, you produced another table and you produced the rule yourself. Good job. All right, now remember how we did the last one that looked like this, number 2. Okay. We have P of L. No, we have P of 11 represents, what does it represent in the situation? So if this were set equal to something, what would it tell us? What would the output of this tell us?
The perimeter.
It would, okay, so P of 11 would tell us the perimeter when?
The side length is 11.
When the side length is 11 feet. P of L would tell us the perimeter when the side length is 11 feet.
That's right. Perimeter, not perimeter. I said perimeter. Perimeter? That's not right.
It's like how when you have to say it like that, so you know how to spell it. That's what I have to do for Wednesday. All right. Next question says, what is the value of P of 11? If we have 11 as our input, what is our output? 28.
Oh, we already had that one.
We did already have that one.
No, I didn't have that.
I just put 3 feet or E's in feet, so yeah.
Feet?
I put 3 E's.
All right, last question. We're making great time. We're going to graph it
We're going to the moon.
to the moon. GameStop. On the coordinate plane, sketch a graph of this function. So just a reminder, the function we're doing is P. It's that function we just came up with. Remember, those curvy little letters are L's.
Those are L.
Let's go.
That's not how I use my L's.
Do what?
My L's are different.
If you do a capital L, that's liters in math, so you can't do a capital L. Okay, so let's graph it. Our input, once again, is our side length. So I'm just going to use all of these values that they already have in order to calculate my perimeter. Okay, now I want you to think about this one before you shout the answer in, because this time we have a different equation. We have a side length of 0. So that means we're going to substitute 0 in for L. So that's 2 times 0. But then we have plus 6. 6. So if our input is 0, what is our output?
6.
So that's right above that 5. Now the reason that is because that paper is always going to be 3 foot wide.
I'm so off.
Okay, what if our input is 1? What is our output going to be?
8.
8. All right, what about if our input is 2? All right, what if it's 3? 12.
What?
Oh.
Add
Earlier he said 18, and then, well, no, he said 12, it was 18, but now he says 18.
Because 2 times 3 is 6, plus 6 is
I thought
12.
we were going on this graph.
That was for area. This is a completely different one. I made that one a little too low, but it's okay. All right, what if the side length is 4? What if it's 5?
16.
So you're just going up by 2, really?
Yeah.
We are. All right, what if it's 6?
18.
All right, what if it's 7? No,
No, it's 20.
it'd be 20. And then finally for 8,
22.
22. Okay, so this one is a little bit different. Had I not been human and could graph it perfectly, what would this one form? It would form a straight line. I'm going to try to draw a straight line through it. Imagine all these are, they landed on the line. Okay, so focus, Lake and Kai, focus. In the last one, we had an exponent in our rule. This time we don't. I want you to think back to what we know about linear equations. What do you know about the number that's right next to the variable? What's that called?
Variable.
What's the number that's right next to my variable? Back to linear equations. When you're graphing equations, the number paired with my x, or in this case L, is my slope.
Look,
Oh, that's right.
And the number that's all by itself is the y-intercept. Look at my y-intercept. What is it? 6. Someone even said it when we were doing it. What's it increasing by each time? 2, which is my slope. That means it's going up 2 over 1, up 2 over 1. Okay? Because that one doesn't have an exponent, so it works just like what we know graphs or linear equations work like. All right, now we have our lesson summary. I'm on page 157. All right. Some functions are defined by rules that specify how to compute the output from the input. These rules can be verbal descriptions or expressions and equations, okay? So like when it says verbal descriptions, that's like what we did in that second activity where you matched them with those sentences. And then the equations are everything else we did. All right, so here's rules in word form, and here's rules in function notation. We should be able to look at both of those and understand how to interpret those. All right, some functions can relate to quantities in a situation, can also be defined by rules, and can therefore be expressed algebraically using function notation. Okay, so here it gives us an example in this last little bit. Example. All right, so we have this situation here. We have function C. What's the name of this function? C. And when that's set equal to something, it gives us the cost of buying in pounds of apples. Okay, so what's my input? In, which is the pounds of apples. That are $1.49 per pound. We can write this rule like this. C of n equals $1.49 n to define function C. So let's break that down real quick. What does C tell us? The function name. The number inside the parentheses tells me pounds of apples, which is my input. All right, so if we take all of that and set it equal to something, what's it going to tell me? The cost, okay, of buying however many pounds of apples we want to get. Okay, so if we were to get 1 pound, we'd just do that times 1, and it would produce our output. Okay, if we were to buy 15, what would we do with the price? Multiply by 15. All right, so that's exactly what they show you in this table here. So you can represent functions in these tables. And once you have those tables, you can represent it graphically. Yes, sir.
You get 10 chicken nuggets at Burger King for $1.49.
Ooh.
They're actually not that bad.
It'd be 16.9%.
There you go. All right, so that is all for lesson 4.